Hi friends, you have heard about the iPhone, iPad, iMac. Do you know what does I stand for in these names? I stands for Internet, since these devices have built-in Internet connectivity. Today in this video, we are going to talk a lot about I, but this is a different kind of I in mathematics. Here the symbol I is called iota and it is used for imaginary numbers. So are you ready to dive into the imaginary world where we'll be talking about imaginary numbers and complex numbers? And I'm going to make these complex concepts really easy for you. So make sure you watch the video till the end. And before we begin, I just want to say, do check out the full courses on our website and Android app. I'll put the links below. So let's dive into our imaginary world. Numbers, numbers and numbers. Our life is full of numbers. We use so many different types of numbers that in the number system, we want to classify or divide them into different types of numbers. For example, you have heard of the natural numbers which are denoted by n. These are your basic counting numbers, 1, 2, 3, 4, 5 and so on. So those are your natural numbers. Now if you add a 0 to the natural numbers, these are called the set of whole numbers. So 0, 1, 2, 3, 4 and so on. See, all these numbers are positive, right? Like natural numbers are all the positive numbers. Now if you add negative numbers to the whole numbers, then you get what is known as integers denoted by z or I. So for example, you have -3, -2, -1 and so on. This is an infinite set, right? And same way 0, 1, 2, 3. So all these are integers. Then rational numbers you have heard of. What are rational numbers? They are those numbers which are in this p by q form, the fractions, right? So rational numbers means the numbers which are in p by q form and they are denoted by the letter q. So for example, 2 by 3, -1 by 5, 7 by 6 and so on. These are all rational numbers. In fact, even these are rational numbers. So 2 you can write as 2 by 1. Okay. So rational numbers contains all these guys. And then you have the irrational numbers denoted by q dash. And what are examples of irrational numbers? The surds or the radicals. For example, √2, √5, √7. Why are these irrational? Because they form a non-terminating, non-recurring decimal. So if you try to evaluate them, the decimal number will be non-terminating, non-recurring. So now if I tell you all these numbers that we talked about together, which set do they fall into? That's right. This is the set of real numbers. So all these things belong to the set of real numbers. In fact, real numbers we can divide it into two parts, right? Rational numbers and irrational numbers. So rational and irrational. So besides this, are there any other types of numbers? The answer is yes. The non-real numbers, which we call as imaginary numbers, and then we'll also talk about complex numbers. So let's take a look. To understand imaginary numbers, let's start off with a very simple example. If I ask you what is square root of 4, you'll say that's simple. Square root of 4 is 2. But remember, we should actually write plus minus 2 because 2 times 2 is 4 and minus 2 times minus 2 is also 4. So if you do 2 times 2, you're going to get 4. And if you do minus 2 multiplied by minus 2, the minus sign cancels and you get 4. So this is simple. You'll say we have not done something like that, or maybe it's not defined, but that is the new thing we are learning here today. But now if I ask you, what is square root of -4? What do you guys think? So some of you might be thinking that let's pull out that negative sign and the answer will be -2. Is that correct? No, because if you do -2 times -2, the answer is 4. But we want -4. So this is definitely wrong. And some of you might be thinking that till now we have studied that whenever you do square root, it should be a positive number, right? Because if you do square root of a negative number, it will be not defined. But that is the new thing we are going to learn today, that if you do square root of a negative number, what are you going to get? Let's take a look. So we'll start with square root of -4 and I will first write it like this. 4 is 2 times 2. and we can't pull out this negative sign. So guys, what is square root of 2 times 2? Obviously it will be 2. So the 2 comes out and we are left with this guy minus 1. Again the same problem. We have a square root of a negative number, which till now we know is not defined. But this is where the mathematician Euler said that square root of minus 1, he said, we are going to define it as I. We are going to say this is our imaginary number, which he actually called iota, represented by the symbol I. So what is our final answer here? Square root of minus 4 is this new imaginary number, which is equal to 2 times I. This is the world of imaginary numbers. So to understand what is the imaginary number I, or represented or known as iota, it is represented by this I. It is basically your square root of minus 1. So you're going into this new world of numbers where you can take square root of a negative number. So obviously if you are having square root of minus 4, that is basically 2 times I, right? Or if you take square root of minus 9, what will it be? 9 is 3 times 3. So this will become 3 times I. Or square root of minus 25, 5 times I. Or I should say 5 iota. I have the habit of saying I, but strictly speaking, this is typically pronounced as 2 iota, 3 iota, 5 iota, right? Or later we'll see, we also write it as I3, I5, right? So the notation, whatever you're doing, you're following in school, you can use that. But this is basically your imaginary number where we are defining square root of minus 1. Another way to understand imaginary numbers is using quadratic equations. You've all done quadratic equations, remember the guys with the x square term in it. So if I give you this simple example, can you solve this equation for me? X square minus 1 equal to 0. This is a quadratic equation. So one simple way to solve it is you just write down the factors of this, right? So x square minus 1, we can use a square minus b square formula. So it's going to be x plus 1 times x minus 1 equal to 0. And so what are we getting? X is equal, so either x plus 1 equal to 0 or x minus 1 equal to 0. So we basically end up with x equal to 1 or minus 1. So that's the answer of this equation. Or another way you can solve it is you can take the 1 on this side, x square equal to 1, and so obviously the roots will be square root of 1 will give you plus minus 1, right? Because the other way you could have thought this is x square equal to 1. So x is square root of 1, which means plus minus. In square root you take a positive and negative. So basically you're getting the answer as plus minus 1. There you go. Now if I give you another quadratic equation, x square plus 1 equal to 0. Now even before you solve this, you can see that there's something strange going on, because 1 is a positive number, x square, square of a number should be a positive number. So how can you add up and get 0, right? Both are positive. So this is where imaginary numbers come in, right? So if you break this down like this, and because we know we cannot factorize x square plus 1, we don't know the factorization of x square plus 1, we know factorization of x square minus 1, as I showed you over here. So the thing we can try out here is we can write x square equal to minus 1. So what is Mr. X? Mr. X is square root of minus 1. And when you're doing square root, again you can put a plus minus over here. And who is this minus 1 guy? Square root of minus 1 is exactly what Euler defined, like we talked about in the previous slide. This is your imaginary number represented by iota. Okay, so basically x equals plus minus, and this guy is your iota. So this is the definition of imaginary number. Please understand this iota is basically square root of minus 1. So basically to solve this quadratic equation, because before that they said, hey, it can't be solved because how can you get 0 when you have both positive numbers? But then they said, okay, we are going to define this new world of numbers where square root of minus 1 is represented by an imaginary number, something that we've never done before, right? So that is basically your x. So if you understand, you can also say another way to talk about the imaginary number is the square of the imaginary number. What is I square? I square is going to be minus 1, because see, I is square root of minus 1. So if you take square of I times I, you're going to get minus 1. And that makes sense over here, because if you put minus 1 plus 1, see, it is satisfying the equation, it is 0. And here you can see I put a plus minus I because we are solving quadratic, so there should be two roots. So two roots of this equation are worked out to be x equal to plus I, or plus iota I should say, and minus iota. I usually like to call it I, but you might keep hearing it as iota as well. The correct thing to say is iota, but you know, like we do iPhone, iMac and all this stuff, this is our I. Of course, those are not imaginary numbers. Those quadratic equations were very easy. Let me give you a slightly more interesting quadratic equation. So let's say you have x square plus 4x plus 2 equal to 0, and you need to solve that. So one method we have learnt is to factorize, right? To find the factors over here and solve for x. But remember, sometimes factors are difficult to find. So then what is the formula that you apply? The quadratic formula, or what is also known as the Sridhar-Acharya formula, right? So what we can do over here, if you cannot factorize it, remember we can use this Sridhar-Acharya formula, minus b plus minus square root of b square minus 4ac. This was our discriminant, divided by 2a. If you use this formula, you can get the factors of this equation. So why don't you try it and apply the quadratic formula and get the solution for this equation, that is the roots of this quadratic equation. So what did you get when you solved that equation? So remember, when you're applying Sridhar-Acharya formula, you're comparing this quadratic equation with the standard form, ax square plus bx plus c equal to 0. So what are your coefficients? A, you can see, is basically going to be 1 over here. A is the coefficient of x square, so a is 1. B is 4 plus 4, sign is very important, and c is 2. So we have noted down these values. Now you just have to plug it into your formula, which is minus b plus minus square root of b square minus 4ac divided by 2a, the famous quadratic formula or the Sridhar-Acharya formula. Just substitute it here, and when you substitute the values, you can see you'll get minus 4 plus minus square root of 8. Now 8 you can represent it as 2 times 2 times 2, so you'll get plus minus 2 root 2 over here, and if you divide by 2, these are the final roots we are getting, minus 2 plus minus square root of 2. So see, quadratic, we are expecting to get 2 roots over here. You have that plus minus, so the final 2 roots are minus 2 plus root 2 and minus 2 minus root 2. So these are the roots of this quadratic equation. Now this was simple, you have done it before. So why was this simple? Because in the square root we just had a positive number here. Remember, what is this square root? It is called b square minus 4ac is known as the discriminant, and here it was greater than 0. So this was pretty easy. Now let's take a look at another example. And remember what we used to call these roots? These are called two distinct roots, because you have distinct roots here, and these are real roots because these are real numbers. They are made of this. They have an irrational part, but these are two distinct real roots. Now let's take a look at our next example here. Now why don't you try solving this quadratic equation? Again, you'll see that factorization is a bit difficult here. So maybe we can again apply the quadratic formula, the Sridhar-Acharya formula, which is x equal to minus b plus minus square root of the determinant, which is b square minus 4ac divided by 2a. So if you compare the coefficients with the standard form ax square plus bx plus c, what do we get? So this is our a is going to be 1, the coefficient of x square here. The coefficient of x is b, which is also 1, so b is 1, and c is also 1 here. So everything is 1. Simple. Now let's plug in all these values. So minus b plus minus b square, 1 square minus 4ac, 4 times 1 times 1 divided by 2a, right? So 2 times 1. So here once you substitute the values, you're getting minus 1 plus minus square root of minus 3. So see, this is the difficult part. Because we are getting a square root of a negative number. So what did we used to do here in the quadratic equations? We used to say that it has no real roots. Because that time we were told that square root of a negative number is not going to give you a real number. So that's absolutely right. It has no real roots. But we didn't say that it has no roots. It has roots, but the roots are not real. Because here you can see this discriminant, the b square minus 4ac. That is the important thing, right? The discriminant turned out to be a negative number. It is less than 0. So that is why we said we would stop over there and say this quadratic equation has no real roots. But now we can understand that you can see square root of minus 3 is going to be, that's right, it's going to be root 3i. So it will have these imaginary roots, right? Because square root of minus 3, we know square root of minus 1 is represented by iota. So it is going to be square root of 3 times iota, right? So definitely this is going to be having imaginary roots, or we can say non-real roots. So let's summarize our discussion on the quadratic equations. Remember, you had this very important table about quadratic equations, that what is the nature of the roots. So nature of roots for quadratic equations. And here we said that it was all decided on the discriminant. Remember, discriminant is b square minus 4ac. So if your discriminant is greater than 0, if it is positive, then the roots will be real and distinct. You will get real roots and they will be different, distinct or unequal roots. And we can calculate it like this: minus b plus minus square root of b square minus 4ac, which we represent as our discriminant, divided by 2a. But if your discriminant happens to be 0, then you will get real roots, but they are equal. Because here your square root of d is going to become 0. So each root is going to be minus b by 2a. But if your discriminant, because b square minus 4ac could turn out to be a negative number like we saw in the last example, if that happens, then you do not get any real roots. So we say we don't get any real roots, and this, we have been studying this till class 10, that the roots are none. But this is not true, because the roots are basically going to become an imaginary number, or what we learn is called complex numbers, because it will have maybe a real part and an imaginary part. So here we say that these roots will be complex numbers, because basically they are going to be having an imaginary part. So let's go ahead and talk about what complex numbers are. So till now we have learnt about this magical imaginary number iota, represented as I, and it is basically square root of minus 1. So basically we have real numbers, the regular numbers that we use, and this imaginary number which is square root of minus 1, and you can have multiples of it, right? Like 2i or 2 iota, 3 iota, and so on. But then the mathematician said, let's combine the real world, that is the real numbers, and the imaginary world, the imaginary numbers together. So real numbers plus the imaginary numbers is what is called complex numbers. So they said, let's join these two guys, the real numbers and the imaginary numbers. So if we say a is our real number, so if a is our real number and b times iota or iota b is our imaginary number, if you add these two up, you get your complex number, which is represented by the letter Z. So is this clear? Very important concept. Complex numbers are basically your real number plus the imaginary number, right? So we can say Z equals a plus iota b, a plus ib, or a plus iota b. Let's take an example. So for example, your complex number Z can be 3 plus iota times 2. So 3 plus iota 2, right? Or 3 plus I2, whichever way you want to pronounce it, right? So you can see it as a real part 3 and an imaginary part over here, iota times 2. Or you can also write this as In some books it is written as the iota is written later, so we write it as a plus bi. Same thing, complex number z is a plus b times iota. So whether you want to write iota b or b iota, that's up to you. So just follow the convention that is used in your school. So again here the complex number z basically is 3 plus 2 iota, if I use the same example. Real plus an imaginary part, this is exactly what is your complex numbers. So complex numbers is like this superset which contains both real and imaginary numbers. But note that sometimes, even just 2i is also said to be a complex number where the real part is 0. So there's no real part. So we can say 2 iota is an imaginary number, or we also call it a complex number. Other examples are like if you take 5 minus iota 7, right? So 5 minus i7, that's a complex number. 4 plus iota root 3, that's a complex number. Then you have minus 8 iota, right? I said if it's purely imaginary, that's a complex number. 3 minus 7 by 11, right? Times iota. All of these are examples of complex numbers. In fact, even 4, 5, these are complex numbers because you can say the imaginary part is 0, but we don't call them complex numbers. We don't want to make our life complex. We just say that they are real numbers. But note here, sometimes the imaginary numbers are usually just represented as a complex number with real part as 0. And so this entire set of complex numbers is denoted by capital C. So this is one important convention, that the set of complex numbers is denoted by capital C, but usually when we write the complex number, we do not use C. Usually we use Z to represent a complex number. So as we discussed, complex numbers combine both real numbers and the imaginary numbers. So remember, complex number Z can be represented as a plus iota b, right? A plus ib over here. And one very important thing here, this a and b, these are real numbers. So since you have that iota I as the imaginary number, which is square root of -1, a and b should be real. Do not make them imaginary. So this is the standard notation, that z equal to a plus iota b. Now one interesting thing is, z can be purely real. When will it be purely real? When the imaginary part is 0. So let's take an example. If I take the number 5, I can write it as 5 plus iota times 0. So you can see that this ib part, the imaginary part is 0. So then obviously we say the number is purely real number. It is just having a purely real number. In this example, the number 5. It is just real. Okay, so we call that purely real. Similarly, you can have a purely imaginary number when the real part is 0. So this we represent like this, REZ. This means the real part of the complex number, REZ. So if that is 0, then the number is purely imaginary. So for example, if we take just 3i you can write in this form, a plus ib form. It's going to be 0 plus i3 or 3i, whichever one you want to write it. So here you can see that the real part is 0. So when real part is 0, we say it is a purely imaginary number. Clear? So again, remember, complex number is the superset. It can be real number plus an imaginary part, so a plus ib, or you can have just purely real numbers, right, like 5, or you can have purely imaginary numbers like 3i. So that is what complex numbers are. Another notation that is often used in complex numbers is that this real part is represented as REZ. That means real part of the complex number. And this b iota part is represented as IMZ, the imaginary part of the complex number. So in this example, what will be the real part of the complex number? That's right. In this example, REZ is going to be equal to 3. Just the real part. And since you have 3 plus 2 iota, the imaginary part is going to be IMZ is going to be 2 iota. So note this notation. It is the same thing as a plus bi, right, or b iota. Just we want to break it down into the real part, REZ, and the imaginary part, IMZ. Now an interesting question for you. Can you tell me some number which is both purely real and purely imaginary? What do you think? The answer is this special number or complex number 0 plus 0 iota. Why? Because when is a number purely real? When its imaginary part is 0. So here you can see I put the imaginary part 0. And when is a number purely imaginary? When its real part is 0. So this is the real part. So basically in our complex number, this special case 0 plus 0 iota is considered both purely real and purely imaginary. So it's like a special case, and this number you can also write it simply as 0, but we try to write it like this, reminding us that both the real number and the imaginary part is 0, because this is after all a complex number. When are two complex numbers equal? So let's understand with an example. Let's say if you take two complex numbers like z1 equal to a plus iota b and z2 equal to c plus iota d. When will they be equal? When the real part of these two numbers, that is a and c, are equal. So they are going to be equal if the real parts are equal, that is a equal to c, and the imaginary parts also need to be equal. Iota b and iota d should be equal, so I can simply say b equal to d. That means these coefficients here, b and d, should be equal. So when are two complex numbers equal? When you're equating them, you're confident that the real parts should be equal and imaginary parts should be equal, because real and imaginary numbers are like different types of numbers. So each part has to be equal, then only the two complex numbers will be equal. Let's understand this with an example. So let's say we have been given that 3y plus 2x minus y iota equals 7 minus 2 iota. Okay, and you need to find the value of x and y. So see, we have been given that these two complex numbers are equal. That means we can equate their real and imaginary parts. So it should be simple. So what will we say here? The real part is 3y and 7. Compare the real parts of these two numbers. So what can we write? 3y equal to 7. See, I have equated the real parts. So what is y? Y is simply going to be 7 by 3. So simple. Now let's equate the imaginary parts. What are the imaginary parts? 2x minus y times iota, and here there is minus 2 iota. Look at the sign carefully. So I need to equate 2x minus y equal to not 2, minus of 2. Y we've already found, so we can substitute it here and calculate x. So 2x minus 7 by 3 equal to minus 2. So 2x will be equal to 7 by 3 minus 2. So if you take the LCM, you will get 7 minus 6. So that will basically give me 1 by 3 over here. And if 2x is 1 by 3, what is x going to be? It's simply going to be 1 by 6. So therefore, x is going to be 1 by 6. So there you go. So simple. If two complex numbers are equal, that means their real parts are equal and the imaginary parts are equal. That's what we equated here, and we simply got the answer. Now let's look at something very interesting, which is the powers of iota, or you can say powers of I. So remember, what is iota? I is equal to square root of minus 1. Now if I ask you, what is iota to the power 0? I to the power 0, what is it going to be? The answer is simply 1. Why? Because any number to the power 0, any number if you raise to the power 0, it's going to be 1. So this is easy. Now what is iota to the power 1? That will simply be I, right? Iota square root of minus 1. Now if you look at I square, iota square, what will you get? So see, that is the definition. If I is square root of minus 1, that means if you do a square of iota, I square, that is going to give you minus 1, because the square root will disappear. So see, these two are matching. I square is minus 1, that's why I is square root of minus 1, right? Next one, iota cubed, I cubed, what is that going to be? So let's break this down. I cubed is I square times I, and I square we just solved is minus 1, so I'm going to substitute that. minus 1 times I. There you go. So I cube is minus 1 minus I. So simple. So we just broke it down and got the answer. Now if I ask you what is iota to the power 4, I to the power 4, what will you get? So here you can say, we can break it down again as I square times I square. Because I to the power 4 is I square multiplied by I square. And I square we just looked at is minus 1. So minus 1 multiplied by minus 1, what is the answer? The answer is simply going to be 1. So these are some very useful values and you can easily derive it from the basic stuff, right? Now if I ask you an interesting one, I to the power minus 1, can you tell me what is it going to be? So remember, when we talk about this negative power, what are we really talking about? The reciprocal of I. 1 by I. So just like remember, for irrational numbers, we never wanted the irrational numbers in the denominator. We said irrational numbers are irritating in the denominator. Same way, imaginary numbers or complex numbers are irritating in the denominator. So we want to, I won't say rationalize the denominator, but we can say maybe want to realize, make this a real number in the denominator. So that is your trick. You do not want that imaginary number in the denominator. So what will you do? You will multiply the numerator and denominator with I. So what you can do here? You multiply the numerator and denominator with I. So I have not changed the fraction. And guys, what is I square? We just looked at it. I times I is minus 1. So we get I divided by minus 1. So what is the final answer? Minus I. So this is really interesting because we got I to the power minus 1 is simply minus I, just by doing this trick of multiplying the numerator and denominator with I. Now let me ask you another interesting question. What is I plus I square plus I cube plus I to the power 4? I like to call it I. I don't like to say iota plus iota square, right? It's very lengthy, but same thing, right? So what is the answer over here? So what will you get? I, let me leave I as I, okay? I square is minus 1. There you go. I cubed is minus I. I'm just substituting the values we found. And I to the power 4 is plus 1. So guys, what do we have here? I cancels, minus I and minus I, right? They're cancelling each other. Minus 1, 1 cancels. So the final answer is very interesting. The sum of all these guys, I plus I square plus I cube plus I to the power 4 is going to be equal to 0. So interesting. So these powers of I questions are very cute and interesting, and you can get these types of questions in your exam. Now why don't you try this interesting question related to powers of I. So if I give you I to the power 12 plus I to the power 13 plus I to the power 14 plus I to the power 15, what is it going to be? Again, remember, I is your iota, which is square root of minus 1, right? This is our I. So you can see we have bigger powers over here. So will we go down to the basics again? So what we can do interesting over here is, maybe we can take I to the power 11 common. So what will I be left with? I to the power 12 will be I to the power 11 times I. And the next term will be left with an I square, then an I cubed, and then a I to the power 4. And guys, we just looked at this. I plus I square plus I cube plus I to the power 4 is what? You guys remember, we just found this out. The answer is 0. So all you have to do is just substitute 0 here. I to the power 11 times 0. So the final answer is going to be simply 0. Such an interesting question. In fact, you can extend this question to any consecutive powers of I. So if I give you something like I to the power 102, I to the power 103, 104, 105, or any 4 consecutive powers, like it can be 100, 101, 102, 103, anything, they will all add up to 0 because there is a repeating pattern. So what am I saying here? I am claiming that if you take any consecutive powers of I, like I to the power n plus I to the power n plus 1 plus I to the power n plus 2 plus I to the power n plus 3 See, you can always take I to the power n minus 1 common. So the 4 terms will give you 0. That is very interesting. Why? Because you will always get this repeating pattern. Your I, so I is missing over here, right? Because I to the power 1 is not there. So your I minus 1 minus I 1. I minus 1 minus I 1. Every time you keep multiplying with I, you will keep getting this repeating pattern I minus 1 minus I 1. And that is why in this question, as we saw, if you take four consecutive power of I, they will sum up to 0. So very, very interesting result we saw from this question. Powers of iota is pretty interesting. So let's try some more questions here. So here's another question for you. I to the power 4k. So what will you do here? So you can use some exponent tricks here. We can say I to the power 4k is I to the power 4 to the power k. And we know that I to the power 4 is 1. So we are getting 1 to the power k, which is simply 1, because 1 times 1 times 1, k times, the answer is going to be 1. So simple. So see, bringing it to I to the power 4 is very useful because it is simply 1. Now let's try the next question. What do you think is I to the power 15? What will you do here? See, again the trick is when you have these big numbers like I to the power 15, you want to look at it in terms of I to the power 4. Why? Because I to the power 4, as we saw, is very simple, 1. So we can try breaking it down into I to the power 4 times 3, 12 plus 3. See, I'm breaking the exponent 15 as 12 plus 3. And now we know that this whole I to the power 4 times 3 is I to the power 4 to the power 3, right? Because in exponents, just like we did there, 4k means 4 to the power k. So 4 to the power 3 here, multiplied by I cubed. So once again, this becomes easy because I to the power 4 is 1. So we have a 1 to the power 3 multiplied by I cubed. So it is simply I to the power 3. And guys, what is I to the power 3? We just looked at that. Or you can just break it down and remember I square is minus 1. So minus 1 times I, which will give you minus I. So I cubed is basically going to give you minus I. So simple. Now why don't you try the next question, which is I to the power minus 71. How do you do this? So again, remember, negative power means it is 1 by I to the power 71. I don't like negative numbers, so I've written it like this. Okay, and again the trick is going to that to the power 4. Okay, the closest power of 4. So for that, what we can do, since we can multiply the numerator with I, and this will become I to the power 72. See, 71 is not a multiple of 4, but 72 is. So I just multiplied the numerator and denominator with I. So 71 plus 1, it became 72. And we definitely know that this is I to the power 4 times 18 here. 18 fours are 72, right? So basically we are getting I divided by I to the power 4 to the power 18. But basically we are getting the form I to the power 4 to the power k. We don't care whether it's 18, 20, whatever, since it is a multiple of 4 we have got, and this I to the power 4 is very easy. We know the answer is going to be 1. So 1 to the power 18 or whatever, that's going to be 1. So the final answer turns out to be simply I. So what is the trick that you've learned here? What is the important trick? That try to get it to this I to the power 4, because it becomes very easy, because I to the power 4 is simply 1. Here's another interesting sum for you. You need to calculate 1 plus I to the power 100. You'll say, oh my God, such a big power to the power 100. What should we do? Again, you have to use some tricks here. So let's see how we can calculate this question. So first start off by breaking down that power into 1 plus I. So you can see that it is a kind of a plus b form. We know what is a plus b square or a plus b cube. A plus b square is easy, right? So we'll keep it as, we'll break down 100 as 2 times 50. And once again, we'll use that exponent trick, that this is basically going to give us 1 plus I square whole to the power 50. So see, I'm breaking down that power of 100 into 2 times 50. And here you guys can apply your standard a plus b whole square formula. It's going to be a square plus b square plus 2ab. So let's put that down here. So a plus b whole square, so it's going to be a square, so 1 square is 1, plus I square plus 2ab, so that is going to give me 2 times 1 times I, and this entire thing to the power 50. So continue simplifying. What will you get here? I square is minus 1, so 1 minus 1 plus 2I whole to the power 50. So the good news is 1 and minus 1 will get cancelled. It becomes simple there. So finally, what are we left with? 2I whole to the power 50. Now how do we simplify this? So this is like a 2 times I. 2I means 2 times I. So we can break down the power. It's like AB to the power x is a to the power x, or AB to the power n is a to the power n times b to the power n. So I can break this down as, so if we continue solving, this is going to be 2 to the power 50 times I to the power 50. And whenever you see these big powers of I, what should you do? Try to break it down in terms of I to the power 4. Remember why? Because I to the power 4 is simply 1. So what will you get over here? 2 to the power 50 times I to the power, so this is 48, 4 times 12 plus 2. I have broken it down like this, right? So what are we ending up with? 2 to the power 50, and this is going to be I to the power 4 whole to the power 12 times I square, because you have this plus 2 over here. And so this I to the power 4, we know it's going to be 1. So 2 to the power 50 times I square. And what is I square? Or let me write this, 2 to the power 50 times I square. And I square we know is minus 1. So the final answer is going to be minus 2 to the power 50. Of course, the answer is very huge, right? Because 2 to the power 50 means 2 times 2 times 2, 50 times. But obviously, we are not going to write that answer. We're going to leave it in this exponent form. But see how we simplified this. 1 plus I to the power 100 was finally worked out to minus 2 to the power 50. So please use these tips and tricks that I've shown you there, and you'll find solving these questions very easy. Now go ahead and try this question. We want to express the following in the form of a plus iota b, right? So you have been given this expression over here, and you want to express it as a final complex number in the form of a plus ib. So basically you need to simplify this stuff out. So let's start off. So this is the question given, and we'll simplify this bracket. So 3 times 7 will give me 21, plus again 7 times 3. I'm going to write it as iota 21. So again, here you can use the notation what is used in school. If you want to write 21i or I21, both are same. You can follow whatever notation is being used in your school. Okay, so I'm following the notation of the question here, and I've written it in the same form. The next one will be, again, I'm going to multiply it out here. So since iota is there outside, so we'll write it as I7 plus this will be I times I. So that's going to give me an I square here times 7. Okay. So finally, what do you get? Keep on simplifying. So we are going to get 21 over here, and I21 plus I7 will give me I28. And here we have I square. Remember, I square is minus 1. So this becomes minus 1 multiplied by 7. So this term basically becomes minus 7. So if you do 21 minus 7, so the whole idea is to combine the real parts and the imaginary parts. Like here we combine the imaginary parts. Now we'll combine these real parts, 21 minus 7. So that will give me 14 plus I28. So there you go. That's the final answer. So it's very simple. You just have to multiply it out, simplify. And again, remember, you can combine real parts together. You can combine imaginary parts together, but you can't mix them up. So that's why the final answer is 14 plus I28. See, we have got the form that we wanted, a plus ib. So we have discussed about complex numbers and done some questions on that. Now I want to give you a visual feel of complex numbers. So how can we represent complex numbers visually? Now again, this topic may not be in your syllabus, but I think it will really help you visualize complex numbers. Before we talk about complex numbers, remember how do we represent real numbers? Real numbers are represented on the number line. So remember this famous number line where you have 0 in the center, all positive numbers on the right side and so on, and negative numbers here. And we can represent your natural numbers, integers, whole numbers, rational, irrational numbers. They can all be represented on the number line. So this is all for the real numbers, right? But how do we represent complex numbers? The complex numbers, as we discussed, has two parts to it, a real part and an imaginary part. Remember, complex number is of the form z equal to a plus iota b, z equal to a plus ib. A is your real part, ib is your imaginary part. So we cannot represent the complex number on the number line because it can only represent real numbers. How do we represent this imaginary part here? Because there is no representation of square root of -1. So this is where coordinate geometry is going to help us. So just like in coordinate geometry, you have a x and y axis to represent two different things, right? You have a horizontal x-axis and a horizontal y-axis, and these guys are sort of independent of each other, right? X and y. Similarly, in complex numbers, we are going to use these two axes. So this x-axis you can think is like your number line, which is going to represent your real part. So we can say this is our real axis. So this is like you've just copy pasted the number line here. So see all these numbers, this is your 0 over here. Then let's say this is your 1, 2, 3, 4, 5 and so on. So positive real numbers here and negative this side. -1, -2, -3 and so on. So this is our real axis. And perpendicular to that, just like you have your y-axis, this is going to be our imaginary axis. I'm going to write IMG axis. The imaginary axis is your y-axis. And that is going to represent the imaginary numbers. Now, who are the imaginary numbers? So here I will not write 1. This is basically representing I. This is 2i. This is 3i. This is 4i and so on. And similarly here in the negative y-axis or in the negative imaginary axis, you will be having -i, -2i, -3i and so on. So are you guys getting a feel of where we are going? Because complex numbers has two independent parts to it, a real part and an imaginary part. That is why we are using a real axis, the x-axis, and this y-axis, the imaginary axis. We are going to use it to represent the complex numbers. And this 2D plane, just like in coordinate geometry, it is called the xy plane or the Cartesian plane. Here we call it the complex plane because it's going to represent complex numbers now. Or we can also call it, it's known as the Argand plane. So you guys can note that now we are dealing with the complex plane. This two-dimensional plane, also known as the Argand plane. So how do we represent a complex number here? Let's take a simple example. So let's say the number you have is, you take the number, complex number z as 3 plus 2i. Okay. So how will you represent it here? 3 is your real part. So you go 3 on the x-axis, right? And 2i, you have to go 2 on the y-axis. So do you guys agree that the number is going to be a point here on this two-dimensional plane? This is the number z we are talking about. 3 plus 2i. Clear? Let's take another example. Let's say you take a number like this. Z equal to 4 minus I. Where will this number lie? So you go 4 on the real axis, 1, 2, 3, 4, minus I, minus on the negative on the imaginary axis. And here you can see your number will be here, 4 minus I. So are you guys getting the idea? We have gone beyond the number line. We are now using two lines, our real axis and imaginary axis, to represent complex numbers. So this gives you the visualization that complex numbers are really two-dimensional numbers because they have two parts to it. So it always helps to keep this concept in mind. Now what about 0 here? If you look at this point 0, this is not simply 0. This is 0 plus I times 0, right? Or 0 times I, whichever way you write it. And that is why you can understand the point we discussed, that 0 is purely real and purely imaginary because it is lying at the intersection of the real axis and the imaginary axis. There's only one number like this which is at the intersection, the meeting point of the real axis and imaginary axis, and that is why it is purely real and purely imaginary. And if I give you any other number like this, like if I tell you what is this number, you can easily read it off, right? You look at the real part, so that's minus 2. You look at the imaginary part, that's 3i. So you can easily represent this number, minus 2 plus 3i. So this is the geometrical representation of complex numbers on the what is called the complex plane, or also known as the Argand plane. So hope this visualization helps you understand what are complex numbers and how they are different from real numbers. And just like in coordinate geometry, remember we represent a point using the x and y coordinate. So you can use that same notation here for complex numbers. So what will this complex number 3 plus 2i become? We can denote it as 3, 2 on the Argand plane, where this is the real part and this is the imaginary part. So basically 3, 2 on the Argand plane represents the complex number 3 plus 2i. Don't forget about i. Similarly, what is this number? This number can be represented in coordinate notation as 4, minus 1, because this is basically your minus I. So here I've represented the axis like this to explain the concept. Many times this will just be the imaginary axis and it is simply written as 1, 2, 3, 4 because you know you're multiplying it with I. But here to explain the concept, I wrote I for you. So similarly, this 0, this special number becomes your 0, 0, and this number in coordinate notation will become minus 2, 3. Again, see the first coordinate, the first value will be the real and the second will be the imaginary, because remember it is an ordered pair. X, y is not same as y, x. So please remember to always write the real part first. The real part of the complex number comes first and then followed by the imaginary part. Clear? And here we usually do not write I over here. It is simply the numbers and we know that we have to multiply with I. So I hope this visualization of complex numbers on the complex plane or the Argand plane has helped you understand them better and see that how they are different from real numbers, which simply lie on the number line. But complex numbers lie on a two-dimensional plane because they are like two-dimensional numbers. Now that you know about imaginary numbers and complex numbers, I have a riddle for you. You have heard of the engineering college IIT, right? So can you tell me what is IIT plus T? So you need to tell me what is IIT plus T, and do let me know your answers by putting it in the comments below. I hope you can solve this riddle and let me know your answers by putting it in the comments below, and I promise to reply to your answers. So friends, I hope the concept of imaginary numbers and complex numbers is crystal clear to you now. And if you enjoyed this video, do hit the like button and share it out with your friends. And if you haven't subscribed to our YouTube channel, come on, what are you waiting for? Smash that subscribe button right now and click on the notification bell so that you don't miss out on any of our videos. And do check out the full courses on our website manochaacademy.com and our Android app Manocha Academy. To make it easy, I'll put the links below. We have courses on physics, chemistry, biology, maths, coding and artificial intelligence. In our courses, you're going to get live classes, interactive videos, quizzes, questions, mock tests and revision notes. So guys, what are you waiting for? Do check out the links given below and do share it with your friends. So stay connected with Manocha Academy and just keep learning.